Hello, everybody. Today I'll be doing questions on electric fields and gravitational fields. So I can show you how to apply all the formulas and how to think for the questions that come up in your examinations. So let's get started. So first off, I apologize for the poor working. I just couldn't. It's an easy way. It's an easy way for me to showcase my how to think and how to use the formulas. So please bear with the poor I guess, production quality. So gravitational field strength, it's force per unit mass at that point or at a point. Remember, 1 mark for definitions. You should definitely get this. Just it's very simple. You just have to memorize it. All right. So in the next question, we have a sphere. A spherical planet has a diameter of 1.2 times 10 to the power 4 kilometers. Remember, you have to convert this to meters, and that's what I did over here. The gravitational field strength at the surface of the planet is 8.6 newtons per kilogram. And using the formula where G equals to F by M, and then you simplify this formula to give you GM over R squared. And then we have to find the mass of the planet. So we know G is a constant, which is 6.67 times 10 to the power minus 11 and 1.2 times 10 to the power 7 meters. I converted this into meters and then divided by 2 because this is a diameter, and then squared. And then rearranging the formula will give you 4.6 times 10 to the power 24 kilograms. Next up, we have the potential at point X above the surface of the planet in B is negative 5.3 times 10 to the power 7 joules per kilogram. For point Y above the surface of the planet, the gravitational potential is negative 6.8 times 10 to the 7 joules per kilogram. So like this graph represents, I'm not sure if you can see it clearly, but that is phi at the y-axis and r, or distance on the x-axis, and we know it's inversely proportional. So since point Y would be closer to the planet, as it has a more negative gravitational potential, that's what you can write, and you'll get 2 marks. 1 mark would be for identifying, and the other one would be for giving the reasoning. A rock falls radially from rest towards the planet from one point to the other. So you're dropping from point X to point Y. So we know phi, or gravitational potential, is work done per mass, and work done is mass times change in gravitational potential. So we use negative 5.3 times 10 to the power 7 minus negative 6.8 times 10 to the power 7. And then since mass is not given, we can just leave it as m, small m. And they're asking us to find this final speed. So all the work done will be converted to kinetic energy. And the formula for kinetic energy is half mv squared. And then we can divide throughout by m. And then make v squared a subject, which will give you 1.5 times 10 to the power 7 times 2. And then the square root throughout to give you 5,500 meters per second. Remember, this is 2SF because all the data points in the question are 2SF. That's one question. Okay, this is another one. Okay, so gravitational field strength. It's force per unit mass at that point. Again, this is just memorizing of the definitions. It won't be that difficult. Next up, we have by considering the gravitational field strength at the surface of Earth. At the surface of Earth, it's 9.81 meters per second. Meters over second square. Show that the mass of the Earth is 5.99 times 10 to the power 24 kilograms. And we're given we're told to assume that Earth is a uniform sphere of radius 6.38 times 10 to the power 3 kilometers. All right. Remember that this is kilometers and you have to convert it to meters. Again, using the formula similar to the one before, we just substitute the values in 9.81, 6.67 times 10 to the negative 11, which is the gravitational constant. And then radius squared is 6.38 times 10 to the power 6 because you convert it to meters squared. Rearrange the formula and get 5.9867 times 10 to the power 24. You could show more significant figures, or you could just directly write 5.99 times 10 to the power 24 kilograms and then write proven. All right, that's the way you do the question. Next up, we have the GPS. The Global Positioning System is a navigating system that can be used anywhere on Earth. It uses a number of satellites that orbit the Earth in circular orbits. So we have to use circular motion in this case, equations of circular motion at a distance of 2.22 times 10 to the power 4 kilometers above its surface. Remember, this states it's above the surface, so this will be the radius plus 2.22 times 10 to the power 4. You do not make the mistake of just taking 2.22 times 10 to the power 4 and substituting it in the formula, which would be wrong. It will add it to the given radius of Earth. So again, you must mention this at the start of every question that involves circular motion. So what this denotes is that centripetal force is equal to the force of attraction due to gravity, and then using the formulas, we simplify it to W square, or sorry, angular speed square equals to gm over r cubed. And then using the information that we have from the question and the gravitational constant, and from part 2, we can substitute the mass in. You can substitute capital G in, and r cubed is 6.38 plus 2.22 times 10 to the power 7, which is 2.858 times 10 to the power 7, which gives us roughly 1.30 times 10 to the power negative 4 radians per second. Remember your units. It's good to know them. Usually in your answer key, you'll be given the units next to the answering, like the space, but you need to know them for your own good. Okay, using your answer in part 2, using this value, prove that it's not a geostationary orbit. So what do we know about geostationary orbits? That they have a period of 24 hours, same as Earth. They move from west to east, and yeah, those are two you need. Those two is what you need to know. At least in this case, what we're looking at, what this question is asking you to find the period, and using angular speed is equal to 2 pi over t, and then shifting the power formula around, you can get t equals to 2 pi over the value you obtained over here, and it'll give you 4.80 times 10 to the power 4 seconds. Remember, this is in seconds because SI units, and then you convert it into hours. And then you must give a small statement saying that since the period is not 24 hours, the satellite is not in a geostationary orbit. Okay, the next question is a plane. The planes of the orbits in the satellites in B are inclined at an angle of 55 degrees to the equator. Explain why the satellites are not in equatorial orbits. So, as this question mentioned, it's a global positioning system that can be used anywhere on Earth. So using that and some sort of understanding on your own, you can come up with an answer that says to be able to transmit signals to the polar regions. One of the disadvantages of geostationary satellites is that due to the equatorial orbits, transmission to the polar regions is weak, and so having it inclined at an angle of 55 degrees will allow you to reach polar regions, and hence to be able to transmit signals to polar regions. All right, another question over here. Gravitational potential at a point. Remember, it's another definition question. It is the work done per unit mass to bring that mass from infinity to that point. They will usually give you graphs as such, where the y-axis is phi. Remember, it's times 10 raised to the power 7, and x is in radius. So the question's asking, by considering the gravitational potential at the Earth's surface, which is when the distance is r, determine a value for mass of the Earth. We've already done this in the previous question. So phi equals to negative gm over r. Substituting values from the graph and from your data booklet, you can rearrange the formula to give you 6.0 times 10 to the power 24 kilograms and 2 SF, because all data points in the question are in 2 SF. All right. A meteorite is at rest, and a meteorite travels from infinity towards the Earth. At infinity, phi is 0 and 2r above the surface. Oh yes, the question states that it's at a distance of 2r above this Earth's surface. That means that the distance from the center of the Earth is 3r. Remember, do not take 2r. You'll still get marks, but you will not get the full marks. Delta phi is 0 minus negative 2.1. Using the graph, you can calculate it. So you take 3r, go to negative 2.1 is roughly negative 2.1. And then 0 minus negative 2.1 will just give you 2.1 times 10 to the power 7. And then work done is basically all the work is converted to kinetic energy, so half mv squared. And then total mass is mass. So mass can be cancelled out, which will give you, and then half v squared equals to 2.1 times 10 to the power 7. And then rearranging the formula and taking a square root will give you 6.5 times 10 to the power 3 meters per second, two significant figures. So that's how you solve that question. All right, so in practice, the Earth is not an isolated sphere because it's orbited by the moon, as illustrated by figure 1.2. So you can see the moon is revolving around the Earth. Suggest two changes to the motion of the meteorite caused by the moon. So as you know, the moon's gravitational field will affect the initial path of the meteorite. While if Earth was by itself, it would continue in a straight line. However, if the moon is revolving around it, as the moon moves around it, eventually the meteorite will also be attracted or pulled by the moon, causing to take a curved path or change in direction. And due to the so there's increased attraction, force of attraction. The meteorite will now experience a force of attraction from the Earth and the moon. Hence, there's a larger speed because there's a larger attraction. So that's how you can think of these things. However, multiple answers are acceptable. Just check your answer key in your examiner reports. Next up, we have an electric fields question. All right, so two charges, A and B, have a charge of positive 6.4 times 10 to the power of negative 19 coulombs, and they're separated by a vacuum of distance 12 micrometers. So as you can see by the diagram, point P are situated on line AB. Point P is 3 micrometers from A, and point Q is 3 micrometers from B. To calculate the force of repulsion between the charges A and B. So this is very simple. This is Coulomb's law. And we know that Q1 times Q2 over 4 pi permittivity of space R squared. That's the basic formula. And you just plug in these values and the data, plug in the values from the question and the data booklet to get an answer of 2.6 times 10 to the power negative 17. That's pretty straightforward. Explain why without any calculation, when a small test charge is moved from point P to point Q, the net work done is 0. So we know that point P and point Q are equipotential. And how do you know that? Basically, the distance, since A and B have the same charge, then and point P and Q are like at the equivalent distance from A. It has 3 micrometers from A and 9 micrometers from B. In this case, Q is 9 micrometers from A and 3 micrometers from B. So the positions are equipotential. And there's no work done as there's no change in potential, because work done is charge times change in potential. So hence no work is done. So calculate the work done by an electron, or you could just write, its equipotential points. You will get marks for that too. Calculate the work done by an electron in moving from midpoint of AB to point P. Take note that it's midpoint from AB to point P. So you have to find the potential at P and then potential at the midpoint. Sorry, this is supposed to be potential at midpoint, not potential at P. So potential at P is pretty simple. You have to use the equation, which is Q over 4 pi permittivity of space and R. So using the formulas that we've learned before, we just plug in the values, and you have to calculate potential at P, which is 2.55767, and 10 times 10 raised to the power of negative 3. And then potential at AB is because at the middle of AB, you have it's equidistant from both of them, so you can just take 2 times 6.4 times 10 to the power negative 19, 4 pi 8.85 times 10 to the power negative 12, multiplied by the distance, which is 12 micrometers, divided by 2, which is 6.0 times 10 to the power negative 6, which will give you 1.918252 times 10 to the power negative 3 volts. Now, work done is like I've written over here, charge times delta V, or change in potential. And the question asks work done by an electron. So we know the charge on an electron is 1.6 times 10 to the power negative 19. And then to calculate the change in voltage, 2.5 minus 1.98, because you always minus larger potential to small potential. And then multiply by 1.6 times 10 to the power negative 19, which will give you 1.02 times 10 to the power negative 22 joules. That's all the questions I have covered. Hopefully, they teach you how to think in your examinations and how to use the formula. Remember to revise your graphs, revise your definitions, because they're easy marks that you can obtain. And remember your formula so that you don't make mistakes. And if you ever get confused or you forget what your formula looks like, you can always just form the formula in your working like I've done over here. Just do some quick mental calculation and you can just solve it. Thank you so much for watching this. Please like and share if you found the content useful. If you have any suggestions, please put them in the comment section. I would love to take a look at them. Thank you so much and goodbye.